All right, let's talk about some major landmarks in logic. It's a story about how one spectacular failure, believe it or not, completely reshaped the world we live in today.
So here's the big question we're tackling. How in the world did a massive, century-old identity crisis in math end up building the 21st century? It sounds kind of crazy, right? But it's this incredible story that shows how hitting a total dead end can sometimes be the best thing that can happen. Okay, so picture this. It's the early 20th century. There's this incredible sense of optimism in the air, especially in mathematics. You've got all the world's greatest minds coming together for what they thought was the ultimate intellectual journey. They called it the quest for certainty. And the energy during this time, it was just electric. I mean, you had brilliant minds like Skolem publishing huge foundational work in 1920. Then you have Russell and Whitehead dropping their absolute masterpiece, the Principia Mathematica, between 25 and 27. And in 29, Presburger comes along with his own breakthroughs. It really felt like everyone was racing toward the same single epic goal. And what was that goal? Well, it was nothing short of breathtaking. They wanted to create a single, perfect system for all of mathematics. I mean, just try to imagine that. A framework with zero contradictions, zero paradoxes, a system that could prove every single mathematical truth out there. They were literally chasing absolute bulletproof certainty.
But you know how these stories go. Just when it felt like they were getting close, a massive crack started to form in that perfect foundation. The whole project, the whole dream, was about to come crashing down. And it was all because of one person and one single paper.
And that moment of impact, it came in 1933. A logician who wasn't exactly a household name, Kurt Gödel, published this paper. And at first, it probably seemed pretty obscure, but it turned out to be an intellectual bombshell. It was about to change, well, everything.
So what did he discover? Well, it's known as Gödel's incompleteness theorems. And here's the gist of it. He proved that for any logical system that's consistent and powerful enough, there will always be statements that are true, but that you can never, ever prove using the rules of that system. Think about that. It's like having a sentence that you know is true, but your language just doesn't have the words to express it. It's fundamentally beyond its reach.
The fallout from this was, well, it was devastating. That dream of a single, perfect, all-encompassing system, it was just shattered. And this wasn't some little bug they could patch up later. No. Gödel had just proven, with the very certainty they were searching for, that their entire quest was impossible, right from the very beginning.
So what do you do when your life's work is proven impossible? You pivot. And that's exactly what happened. The old quest, what is provably true, was over. It was dead. So thinkers started asking totally new and honestly more practical questions. Questions like, okay, what is computable? And how do we actually reason with uncertainty? In a really strange way, this massive failure was a kind of liberation. And out of the rubble of that old dream, two big new paths emerged. Let's talk about the first one, the dawn of computation. It was built on this really cool new philosophy. Hey, if we can't prove everything is true, maybe we can at least calculate the things that matter.
And this new field didn't just appear overnight. It was built step by step. First, you had pioneers like Alonzo Church and the great Alan Turing, who basically came up with the definition of what it even means for something to be computable. Then in the 50s, people like Stephen Kleene helped build out the whole field. And by 1971, you've got S.A. Cook digging into computational complexity, introducing core concepts that computer science is still built on today.
And listen, this wasn't just some abstract academic exercise. No way. This pivot from searching for truth to focusing on computation, it laid the direct groundwork for the device you're watching this on right now. The modern computer is a direct, honest-to-goodness descendant of this huge philosophical shift.
Okay, so while one group was off building the foundations of computation, another group of logicians took a totally different path. They had this thought. If perfect black and white logic is impossible, maybe logic needs to get better at describing all the gray areas in between. Maybe it needed to embrace uncertainty.
And a huge breakthrough on this front was something called fuzzy logic, which Loftizadeh introduced back in 1965. The idea is brilliant. Instead of things being just plain true or false, fuzzy logic deals in degrees of truth. It's a system that's actually designed for real-world stuff. Concepts like somewhat warm or very tall that just don't fit neatly into a yes or no box. When you put them side by side, the difference is just stark. Classical logic is binary, right? It's either true or false, 1 or 0. But fuzzy logic, it allows for any value in between. So instead of just saying, the room is dark, yes or no, you can say, the room is, say, 0.8 dark. It's a much more subtle, much more nuanced way of describing the world as it actually is. And Zendaya wasn't the only one thinking this way. This was part of a much bigger movement. For example, in 1982, Zdzisław Pawlak developed something called rough sets, another really powerful tool for dealing with data that's incomplete or imprecise. You can see what's happening here. Logic was finally getting comfortable with the messiness of the real world.
So, okay, we've got these two major new paths branching out, computation on one side and uncertainty on the other. But how did these abstract ideas actually build the world we live in? Let's connect the dots from the theory to the tech that you and I use every single day. Seriously, the impact is everywhere. That computability theory, it gave us modern computers and all the algorithms they run. Complexity theory, that's the bedrock of all our internet security and cryptography. Fuzzy logic, it's powering AI and the control systems in everything from your car's anti-lock brakes to your washing machine. And it doesn't stop there. Other branches, like temporal logic for checking software and quantum logic for the future of computing, they all grew out of the same incredible shift in thinking. The end result was just an explosion of new ideas. Before Gödel's paper came out, all this research was laser-focused on one single narrow goal. But afterwards, the field just blew wide open. It diversified like crazy, first with the birth of computability and then with countless new applications popping up everywhere. The amazing irony is that the failure to find one perfect logic ended up creating dozens of incredibly useful ones. So when you boil it all down, the story of modern logic is really a story of reinvention. And it's a reinvention that was born from a spectacular failure. It's a field that is constantly evolving just by asking new questions. And that really leads us to our final thought to leave you with. What problems will logic's next reinvention end up solving?